Hello everybody, and welcome to the beginning of page 57 in the workbook. We are looking at Theorem 7.1 Lagrange's theorem, and before we dive into the theorem and a proof, I just want to say something about the theorem in general. This is one of the most important theorems in our entire course. The statement of the theorem itself sounds really simple, but it has some far-reaching implications that are really kind of amazing. We're going to be able to do a lot of neat stuff with this theorem. Okay, so let's just read it together and see what it's saying. So they're starting us off with a finite group and a subgroup H of that group. And Lagrange's theorem says this, that whatever the order of the subgroup is, it has to be a divisor of the order of the group. Okay, every single subgroup of a group has to be, its order has to be a divisor of the order of the group. Okay, and then we can say one more thing in the second sentence here. The number of distinct left or right cosets is always going to be given by the order of the group divided by the order of the subgroup. Okay, let's see if we can prove this theorem here. Okay, so we'll start out by noticing that since the group that we're starting with is finite, then the number of cosets of the subgroup in the group is going to be a finite number. Okay, so we'll make a list of all of the cosets that we could get, okay, of H and G. Okay, A1, A2, up to ARH, denote all distinct. I'm going to leave room for a little picture here. I'm going to underline the word distinct. Cosets of H in G. Okay, so we're just assuming that we've made a list and all of those cosets are distinct. And so we can draw the picture that we've drawn a few times already. These cosets have to partition the group. Okay, so we've got A1H up here, A2H. Okay, and we keep going and eventually we come to the last one, which we called ARH. Okay, so there's kind of a visual representation of what our entire group looks like, coset by coset. Okay, and now what we want to do is to kind of make the point that if you take any element A and G and ask what is the coset generated by that element, it's got to be a coset on our list. Okay, so in other words, let's say it this way. For each A and G, the coset AH must be on the preceding list. Okay, and the reason for that is this word all. We made an assumption that that was a complete list of cosets. Okay, so it's got to include the coset AH. Okay, and so what that means, we could say that A is in the coset AH, and that coset's got to be one of the ones on our list. Maybe it's AI times H. Okay, and so what we've really shown then is that every member of G belongs to one of the cosets. Let's write that down. Okay, and so what that's describing then is the fact that the entire group G can be written as a union of all of those cosets. Our picture is kind of telling us that anyway. We've just confirmed that. Okay, we're going to come back to that equation in a minute, so I'm going to give it a name, just label it star here. Okay, so there's our decomposition of G into the cosets. Okay, what can we say about that equation then? Remember how we made a big deal in the coset lemma about how cosets are disjoint. So all of the cosets that we see in this equation that we wrote are disjoint from each other. Okay, let's make that point. Okay, so by part 3 of the lemma, Okay, the cosets in star are all disjoint. And so since they're disjoint, we can get the order of G by just kind of going coset by coset by coset and adding up the order, the number of elements in each of those cosets one at a time. Okay, that logic would not work if there were overlap between the cosets, but because they're disjoint, we can use that strategy. Okay, but notice we also know another thing about cosets from our lemma. Every single one of the cosets on the list up here has the same size. That was, I believe, part 5 of the big cosets lemma. Okay, so let's write that observation in. Okay, since the order of the coset AIH equals the order of H, I'm just going to mention where that's coming from by part 5 of the lemma. For all I, we have, let's think about that before we write this down, basically saying that every single one of the terms that we have here is equal to the order of H. So it's like taking the order of H and adding it to itself over and over and over again. How many times do we add it to itself? Notice that we add it to itself R times. We labeled this last one R. So that means then that the order of G is just going to be R times the order of H. Okay, but notice what that says. We have just demonstrated that the order of H is indeed a divisor of the order of G. It's R times. Okay, the order of G is R times the order of H. Okay, and there it is. There is our proof. Okay, and we will see what fun we can have with this theorem later on.